Okay, I want to thank everyone for joining us this morning in our second webinar for the Build Your NashTran In-CAD IQ session. Today we're going to be talking about getting the data out of your in-CAD analysis. So we'll wait just a minute here as it looks like people are still filtering in, and we'll give them a couple more seconds before we get started. So my name is Andrew Satterelli. I'm a technical support specialist here at Autodesk covering the mechanical simulation products. And with me today is Bart McPheeters, a senior technical specialist for our simulation products on the sales team. And he'll be discussing how to get your data out of NashTran In-CAD. I do want to remind everyone there is a questions box on the side. At any point during the webinar, you can ask whatever questions you may have, and we have staff on hand to help answer those. And there'll also be a 30-minute Q&A session at the end of the presentation to cover some of the questions live. So we'll go on to the next slide here, Bart. So as I mentioned, this is the second webinar in the series of Build Your NashTran In-CAD IQ. 2 weeks ago, we covered what is NashTran In-CAD, and this week we'll be talking about how to get your data out of NashTran In-CAD. Coming up in next week, we'll be doing a session on what's new in NashTran and NashTran In-CAD 2016 with the product manager Mitch Muncy next Wednesday, excuse me. And then in 2 weeks from today, we'll be talking about contacts and constraints, and then in a month from today, we'll be talking about composite analysis in NashTran In-CAD. And all these webinars will be posted on our YouTube channel, Autodesk Sim 360. And for those of you wondering, we do post these announcements about the webinars on the NashTran In-CAD forums through LinkedIn, direct mail. Also go out on our Twitter feed at ADSK Simulation, and on our Facebook page, Autodesk Simulation. So what's new, what's in the news? In case you haven't heard, we did launch our 2016 product line for the simulation products on April 7th, so that did include NashTran In-CAD 2016. So if you're on subscription, I think most of you will be, definitely go ahead and take a look and download that. There's some really great enhancements in that version. So at this point, I'm going to hand the presentation over to Bart, and he'll be talking about how to get your data out of NashTran In-CAD.
Hi there, this is Bart. A little quick agenda. I basically have two topics I'm going to talk about. The files and the file types you can get out of NashTran, and then looking at the results and some of the options that you have to make sure that you're actually plotting what you think you are, and you're plotting what you've calculated, and you have a good idea of what you got. So I'll get started right here. NashTran itself produces quite a few different output file types that are general output. The Outfile that you get when you run a job is a general printed output, and it can have results, it can have other stuff. I'll talk about a lot of the stuff that goes in that. But you always get an output file, and it may have a little or more or less depending on what you've asked for. There's a much older format that I'll talk a little bit about called a punch file, and it's a formatted ASCII output, and I'll show you how to ask for all of these. By default, we produce an FMO file, which is a binary neutral format, and those are the ones we produce by default. We read them into In-CAD, so when you look at results in In-CAD, you're looking at FMO files. But in addition, NashTran historically has produced OP2 files, and OP2 files are an old standard that go back to the very early days of NashTran, and we can produce those as well. And there was a later type of file called an XDB that was created, I don't know, probably 10 years ago, and it has some advantages as well, and a lot of people read them. So those are the types we have, and let's start with the out file. It's general printed output, and there's some stuff that's always in this file. All the parameters, all the directives, anything you change and put around, you'll get an echo of it in the data, in the out file. If you're running a nonlinear analysis, all the iteration data. I often tell people, they say, my job is not converging. How do I tell what's not converging? It's like, well, let's look at the out file, and we'll take a look at the out file and look at the iteration data, and we'll be able to tell it. If you run a modal analysis, you've got eigenvalue listings, and then there's a whole series of summaries of things. Summaries of maximum forces, force resultants, summed reactions, the max reactions, max applied loads, a lot of things like that. Those are always in the output file or the .out file. In addition, there's a number of optional things, and the first one's the weight generator, and I'll talk a little bit about after this slide. You should always do a weight generator. It tells you the model weight, and if you're running through in-CAD, it's the default, and it essentially inserts internally a Peram grid point 0, and grid point's the old grid point weight generator, and it generates and figures out how much your model weighs. It's a nice little check on your model, so it's worth doing. Another thing you can ask for is an echo of your input data, and it'll give you a listing of everything you did, all the grid cards, all the C quads or the C tetras, or all the any entry that you have in NashTran. You'll have a sorted list of that. If you have a big model, it makes a really big output file, but it's also nice. The other thing it does, and it'll actually do by default, is a summary. It'll say I've got 200 bars, 600 beams, 45,000 quads, 3 contacts, things like that. And those are always nice, a little summary of what you've got in your model. And again, those are optional. Most of them are on by default. The weight generator, if you've never had an opportunity to look at it too closely, it's really nice because up here on this matrix, it's a 6x6 matrix that effectively converts your model into a single lumped mass. And up here, notice the reference point is listed as 0. If we went back to our Peram grid point, it's putting in 0, and 0 means find all these masses and moments of inertia about the center of gravity of the model. Where is the center of gravity? Well, down here on the weight generator, it has the center of mass, and so it has in the x direction, the y direction, the z direction. And this is a useful thing in addition to just checking the model. I've had occasions where someone gave me a model and I wanted to represent it as a lumped mass. So I run the model for some static analysis with a grid point weight generator, and it comes out and gives me this matrix. And then I can take this matrix and put it in and replace the whole model with a lumped mass. And these are all the properties, the masses and the moments of inertia. Real nice, real slick way to do it. And the center of gravity tells me where to locate my lumped mass. Further down on the weight generator, there is, let's see if I can get this to work. There it is. Further down, you get the principal rotational inertias. And what it does is they're like principal stresses. It's the largest inertia about the 3 different directions and the 3 different axes such that there's no off-diagonal terms. And it comes up with a little rotational matrix down here. Sometimes you want these. If you have a model that's symmetric, these will be the same as the ones back up here on the corner here. They'll have no off-diagonal terms. But almost all models aren't perfectly symmetric, so you have some cross products. And this converts them to the principals. Sometimes if it's not very asymmetric, these will work for lumped masses. The out file, the reason you have the output file is because what you really want are results in it sometimes. And the results in it, the out file itself is ASCII. If you've ever looked at it, you've realized it's an ASCII file. And it's I'll call it a semi-standard NashTran format. It's formatted for 120 character pages, 120 character wide pages, so you have to print it in landscape. But the format that we use and has been used is relatively the same across different versions of NashTran across many years. And each page has a little header on it, tells what it is, column headings. It's a really nice format if you're trying to look at the output. If you've ever run MSC or NX NashTran, they call it the F06 file. We call it the out file. The results are formatted, they're labeled, they're nice, and the way it's accessed in in-CAD is by choosing print, and I'll show you that in a minute. But what it actually does is when I go up here, if you can see in the upper right-hand corner, I have my output requests for displacement, SPC forces, stress, and notice the first word is print. That tells it to send it to the out file. And so that's how it works sort of internally. I'll show you how to do it in in-CAD. But often, probably not on big models, but often on small models, you want printed result because you're trying to compare to a test case. You want to see exactly what the stress that's being calculated. You need to know what the torsional force is in a bar, for instance. And so by printing those results, you can get something that you can cut and paste and put into something else fairly easily. The results are sorted by result and type. So each element type has a section. The grids have the plate elements have a section. The bar elements have a section. The triangles have a section, and so on. And then each time step, each subcase, each increment, and so on has its own section too. So it's fairly well divided. You can sort things out, cut and paste. And again, the format we're using is a relatively standard NashTran format. So if you have something that reads FO6 files, it'll probably work with an Autodesk NashTran Outfile. Just got to change the name of it. The results, here's sort of a sample. This is a nodal result. This is a displacement vector. So you can see it's got a little, I didn't cut it out here, but you got a little title up here that would be at the top of the page. Tells me it's subcase 1, tells me its displacements, and then a list of the grid points, the coordinate system that it's in, and then displacements in X, Y, Z, R1, R2, R3. And these are all set up however many grids you have. You'll end up with nice sorted printable pages with a new set of headers on each page. Sort of slick. For element results, each element has, depending on what type of element, various different sections on it. Again, you have the title, stresses and quad elements, coordinate system, they're all in. And then it'll start off and it'll give you the element ID. And if you've only asked for center stresses, it'll only give you the center point, the centroid point. Plate elements have a top and a bottom fiber, and it tells you the distance. And then you get normal stresses, principal stresses, von Mises stresses. But if you have asked for corner stresses, which in-CAD produces by default, you'll also get the stresses at each corner node. You can see the same top and bottom. The stresses are different because they're at the corners, they're not at the centroid. The centroid stresses are actually the average of all the 4 corner ones. So if you took this one and this one and this one and this one and added them together and divided by 4, you'd get that. Hex elements have 8 of these. TED elements may have 10 nodes. So again, you can see you end up with a lot of printed output pretty fast. But again, disks are cheap, but it's just hard to look through. The grid IDs, the fiber distance, and then all the results. And so all the elements will have something like that. To get that printed output and put in the out file, down on the, you right-click on the analysis, and I'll show you this a little bit later, and you choose to edit it. And normally you'd be poking around saying, I want to change it from a linear static to a modes or something like that. Instead, down here under output options, you can choose to plot it, which is the default, or print it. And printing is what gives you the out file. There's also a punch and a punch and plot. And I believe we plot all the time, no matter what you ask for, unless you ask for punch alone. Just one of those little sort of weird things. So what actually goes into the file, you choose here. You've probably chose those. We said I get the corner stresses if I ask for them. By default, the corner stress is turned on. So our next file type is a punch file. It's a really old one. You saw how you get it. Again, in your data deck, in your data deck over here, it shows up as punch rather than print. And you can put multiples. You can say print, comma, punch, comma, plot, and get all 3 of them if you like. It's a much older file. It's easily readable with an external program. So if you have a Fortran program and you're trying to read a file, it's really nice to read these instead of the out files because there's no page numbers and titles and headings and columns and everything. It's simply one line that tells you what all the data is, and then the data is thrown out there. People call me all the time and say, can you tell me what the format is for the punch file? And the trouble is, it's not very well documented anywhere. And so what I have a tendency to do is run one and print the output and then plot the output or punch the output and then compare the two, and then I can tell what the data is. Here's a little sample. This is actually the same one we had before, and it tells me the grid number. The G, I think, means it's a grid. This is what we're looking at, or displacements. And then we've got X, Y, Z, RX, RY, RZ, and then we continue on to grid number 2, and we work on, actually I think G is the global coordinate system is what that's in. It's got line numbers out in the end if you want to do it. It's an 80-character field. So it's pretty simple for displacements. You're configuring them out a little easier. Quad elements, it's a little harder. I have a 0 here. I'm not sure what the 0 is. I've got a minus 0.05. This is my fiber distance. And then I've probably got a series of stresses for different nodes and so on and so forth. And again, the format's not documented very well, so if you want to use it, you have to work it. But once you've figured out what it is, it's very easy to read with Fortran, Visual Basic, whatever you do, because you've got this header up here, and then you've got data, 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 until it ends with a end of data marker. The other output files, I'll call the FNO, the OP2, and the XDB. These are all binary result files. Historically, the FNO was developed for FMAP, and we use it for In-CAD. We developed a lot of that in-house with Autodesk NashTran, so it's a format that we sort of own. The OP2 is a generic, ancient OP2 binary result format. Other NashTrans still produce that. There's 1,001 post processors and codes that run as post processors, like fatigue codes and building code analysis tools, and they all read OP2 files. So fortunately, we can produce OP2 files. A few years ago, MSC developed the XDB file that's a relational database format, which is very, very efficient for reading results. We can generate one of those as well. In order to get those on that form we looked at, you choose plot, and that will give you those results. And then which type you actually get is chosen by a directive. There's a NashTran directive called result file type, and then you give it the type. NashTran binary, for instance, is an OP2 file. And you can either go through the parameters box to put this up, and I'll show you that, or you can go through and do this by simply adding a line to your data deck, and I'll give you sort of a quick example of that at some point. In your parameters, it is an output control directive, and down here result file type, and the default is FMAP binary, which is the FNO file that we use for In-CAD. There also is NashTran binary, which is the OP2 file. There is I would call it a FMAP ASCII file that's a FMAP neutral file result format. The FNO is the one we used, FMAP binary. Down at the bottom here is the XDB file, and there's a whole series of these DIS and ELS files, and there's one version that Peram uses, and there's a different version that Autodesk NashTran creates, and they're very, very similar, and you can choose those. For the most part, though, stick with the OP2, the FNO, or the XDB. Those are the ones that people use most of the time. Occasionally you see the neutral file, but those are the three that people use most of the time. OP2 files have additional options for compatibility with other programs. And people say, isn't an OP2 file an OP2 file? And yeah, it is, but it isn't. Different programs require different data blocks written in different orders in different ways. And so we have a parameter called param post. And param post sets up a number of different ways. If you want an OP2 that's compatible with Peram, you put param post -1. If you want one that's compatible with anaglyph laminate tools, you put -8. Unigraphics uses a -6. Ideas uses a -2. So these are, you'd set param post to do that. If you're ever curious what it actually does, in the online documentation, the geometry data blocks, some of the different parameters print out geometry data blocks, grid point definitions, element definitions. Some of them don't. And this is just sort of a comprehensive list. If you don't know what your program uses, you can put -9 or -10, and it will do all of them. And the same is true when I do results. These are the different results data that come out. You notice number 4 doesn't do any of them. Number 4 doesn't do any results. And the others are pretty similar, except composite element stresses don't get written out for post -7. And again, 9 or 10 does everything. So these are just sort of the tables. You don't have to memorize them, but they exist, and if you want to know what your code uses, you can look it up. Now I'm going to go to second topic here today, the results themselves. There's two types of results that are available to you that come out of NashTran or that come out of that are available in In-CAD, and those are nodal results. And by nodal results, we generally mean quantities that are calculated at the nodes. Displacements, for instance, are always calculated at the nodes. Constraint forces are always calculated at the nodes. Applied loads are always applied at the nodes. So those are formally what we call nodal results. The other results that come out are elemental, that are come out and they're produced on an element-by-element basis. Stresses, element forces, layer stresses, composite forces. Those are all elemental values. In-CAD, on the other hand, can plot nodal results for stresses. And so the question then becomes, what the heck is it actually doing? And what it's doing is mucking around, and hopefully the couple slides here, and I'll be able to show you exactly what NashTran is doing for this kind of stuff and what In-CAD is doing. So NashTran calculates 4 elements. They calculate centroidal results, which give you one result for an entire element. They also can calculate corner results. Again, this is the default, and centroidals are always calculated. Corners are sometimes calculated if you tell it. And when you get a corner node, you have one result for each node attached to the element. So a quad element will have 4 corner stresses or corner forces. 10 element will have 10 of them. In an ideal world, I have 2 elements that are next to each other. The centroidal stresses I wouldn't necessarily expect to be the same, but the element corner stresses, I would, in theory they should be the same. If this element says it's 110 at this corner, this element should also say it's 110 at a corner. Unfortunately, that's rarely true. You end up with 2 different results at that corner. So this corner said one element thinks it's 110, the other thinks it's 100. So this is normal, but if we're going to plot stresses as nodal stresses, we have to come up with a value at that node. And the typical way to do that, which is the default, is averaging. So in this particular case, there's 2 elements. One says it's 110, one says it's 100. So In-CAD is going to declare it's 105 because it's going to average them. It's the default. It's called stress averaging. Every preprocessor on the planet does it, and most of them do it by default. In addition, In-CAD has the option, and many others do too, but In-CAD definitely has the option of choosing, instead of the average, choosing the max. So it looks at 100 and 110 and says, the big one's 110, so that's going to be my nodal stress. Likewise, you can choose the minimum. I'm not sure why you'd want to choose the minimum, but you can. In-CAD also has options to plot these results. You have nodal contours that convert element results to nodal results using one of the methods we just showed, or In-CAD has an option to plot elemental contours or element contours, and there you have a single value for each element. And I like to joke it's the Rubik's Cube plot because each element is a solid color and elements next to each other may or may not have the solid color, so it ends up looking like a big Rubik's Cube. But anyway, each type can use centroidal results to calculate my elemental or my nodal, or they can use corner results to calculate those. And again, the result can be averaged, max or min, so on and so forth. So it gets a little complicated. Here's the default. here's our form. My data conversion is listed as average. So it's going to look at the values that it gets. It's going to average the ones together for different elements, and it's going to come out with the average, and that's what it's going to use. I'm telling it to use corner results. So it's going to take the element corner data, and it's going to average those values together instead of using the centroid data. And then when I plot it down here with a contour type, I'm going to plot a nodal contour. So the nodal contour is going to have values at the nodes and little contour lines that go between them plotted across the elements. So that's the default. Here's the kind of thing we get out of this. Here is a stress value. I'm plotting, I think I'm plotting Max von Mises stress top or bottom. And it comes out, tells me the max is what, 156,700. And it's at node 548. I can hover over that with my query display and figure out what it's actually plotting me. And so what it's doing, by default, it's taking these four elements and it's looking at the corner stresses at this common corner at node 548, and it's going to average those together to come up with 156,700. Alternately, if I change it to a max conversion, it's going to do exactly the same thing, but it's going to look at those four values at that corner, and instead of averaging it together, it's just going to pick the highest one. So in this case, it's 157,200. So it picks the four. When I hover over this with my query display, be careful that in-CAD shows you what in-CAD is actually plotting. It's not showing you the element results. It's plotting it's telling you what in-CAD is plotting. So it's a little thing that's a little bit different than what NashTran actually gets. And speaking of what NashTran actually gets, we were interested in node 548. That was the one of interest here. And nodes 207 and 208 are above and below each other. There's two other nodes that are on the other 90-degree section, but everything is symmetric, and so those two elements are the same. So when I did the average, it looks at 548 from element 207, it looks at 548 from element 208, and it averages the two of them together, and it comes up with 156,700, which is the value we got up there. When I tell it to do the max, it says this one down here is bigger than that one, so 157,200 is the value I'm going to plot. So the max just chooses the biggest of them. I'm showing you with two elements. There's actually four. For element results, it's the same sort of deal. You got these corner calculations, and when you go to element results, I'm picking one value for the whole element. And so I have a center value, and I'm going to ignore my corner nodes, and I'm just going to take the center value. And notice that that center value, it was 150 something before, now it's 130,000, and that's because it's averaging these. Here's our 156 that was the high value, but it's being averaged with a couple down here that are 116, 115. So you average those together, you get about 135. So when I plot element results instead of nodal results, or element contour instead of nodal contour, my results are always going to be lower because I'm averaging the four nodes. Actually, the center nodes here are calculated as the average of the corner nodes anyway, so if you average this and this and this and this, you'll get that. So same idea. If I plot my centroidal values, they look like this. I'm just doing the centroid. I'm not doing an element contour. I'm just doing a centroidal. If I change it to not averaged, then I get the peak value that any particular element has. But it's still drawing a nodal contour because it's calculating the values at the points. So I'm going to do a little demo here, but you've seen how to get the different file types. You know what you're looking at in in-CAD. You've seen sort of how our element averaging and elemental versus centroidal plots. I haven't talked about top and bottom surfaces, but I'm going to talk about that. And we've talked about element results versus elemental results, nodal results versus elemental, as compared to elemental plotting versus centroidal or nodal plotting. So with that, I'm going to bail out here and go to a little model. Those of you who were here last week probably recognize this model. It's the flat-walled tank from the training exercises. And And this is not good. Let's start this up again and open up my model. One of the things that we do a lot of in In-CAD and NashTran is NashTran's a very sort of text-intensive program. And because it's sort of a text-intensive program, I'm forever looking up to find out what things mean. And so I was going to sort of show people where to get the things. In 2016, we've gone to an environment here. And I do not have a model running. Let me see if I have one that I have. Oh, I know what I can do. This is not going to work, I don't think. Nah, because I don't have a mesh. Oh, crud. Let me pull up a different model then.
Bart, while you're doing that, I think we got a few poll questions we can throw out to the audience here.
That would be awesome.
So let's do this first one here. So here, what is your CAD program or package of choice? Are you using Inventor, SolidWorks, CATIA, Creo, maybe using Rhino or something else? So we'll give a minute for everyone to vote here. It does look like the majority so far are Inventor users.
Okay.
Looks like there's a few SolidWorks users out there as well.
Well, In-CAD works in both, so that's always a good thing to have.
Go ahead and close that, and we'll just share those results. So it looks like 91% of you are Inventor, and 9% are using SolidWorks. Okay, and we'll take a look at, watch this. So have you used Nastran In-CAD before? You know, maybe this is your first time taking a look at Nastran In-CAD with this webinar. Some of you may have dabbled around in it a little bit. Others of you may be using it in a production environment. Maybe you used it when it was called NeiWorks. So what's your experience level with the product? Right, so far it looks like majority of you have used it a little bit. Looks like a few of you are using it quite often or almost every day. So we'll leave the poll open for another couple seconds here. And share those results. Yeah, so it looks like there's a couple users here that are using it quite frequently. We've got a lot of people that are just using it a little bit, and there's a few of you trying to learn probably more about what is Nastran In-CAD and understand how it can kind of fit into your workflow. Okay. So let's see, Bart, do you have the, there we go. Looks like you're all set up there.
Yep, I got a different model. This is a fun one. This illustrates some good things here. I'm liking my new little mouse here. By default, when you go to plot something, let me go here. By default, when you open it up and say plot something, you almost always get a plot that looks like this. Because by default, In-CAD plots displacements. And if you plot deformation, it plots percentage rather than actual. This particular model is showing a press fit analysis where the two parts actually overlapped each other in the CAD and Inventor. And what I wanted to find out was what kind of a stress I get when I heat one up and stick it around the other one, cool the other one down, and then let it expand. I end up with a press fit situation. So it's a nonlinear analysis, and you obviously don't get this big gap in a deformed shape. So it's always nice to change your deformation scale to actual. So now the actual deformations are shown, which are considerably less. So that's pretty cool. But the other thing I'm always interested in is instead of displacements, I always like to plot the stresses. And so I'm going to choose the solid von Mises. Von Mises are nice. This is made out of steel. And so here's my default plot. And Notice again, it's an average. So I'm averaging adjacent elements together. I'm using corner results, and I'm plotting a nodal contour. So probably the biggest change that I can change here is average the peak value on here, what is it, 1.5 million or something, high stresses. I can change it to maximum instead of average, and it actually goes up. And that tells me there's two elements that are estimating different values at one point, and they're estimating fairly different values. The minimum down here is probably going to be, what, 1.3, 1.3, 1.4 million. So average is, that's the default. It's not necessarily a bad thing, but someone who looks through your printed output or looks through your summary is going to look through the summary and say, hey, it says that I have an element that's 165, and you're showing me a plot, and the plot only shows 155. What gives? Well, it's just how you're presenting it here. The other thing we've got is we're using corner results. If I switch to centroidal results, again, the results drop quite a bit. And a reason why is, in this particular one, notice I only have two elements through the thickness here. So I have a stress gradient that's going from fairly high out here to fairly low through two elements. For 10 elements, that isn't really a very good, it's not really a good enough mesh to resolve the gradient very well. So it doesn't surprise me that the centroids are different, especially since this element, for instance, the centroid is here, which is quite a ways up in the gradient. The centroid for this element's up here. So the centroids are quite a ways away from the high stress point. So I'd have to question whether using centroid stresses made all that much sense for a case like this. The other thing I can do is change from my contour type from nodal to elemental. Well, when I do that, I now get my Rubik's Cube plot, or I will if it does it. Let's draw this here. Let's turn off my averaging here. Sorry. There we go. So now I've got my Rubik's Cube. And you can see, again, this element and this element, because the centroids are quite a ways apart from the stress gradient, actually show fairly different values. And this is not atypical of a 10 element mesh, but it sort of shows you that the elemental whole element versus the nodal where it tries to average them together and draws a nice plot. The nice thing here is if I plot the corner stresses here with the elemental, it's going to pick out the average of the four corners, which is the same, or I can tell it to pick the max of the four corners and plot that to represent each element. So once again, our max here is the 1.6 because that's the maximum value, and it's plotting the elemental, the maximum of them all. So those are some of the things you can do. The averaging here, if you're using plate elements, it's always nice on averaging to average across properties, to not average, because if you average across properties, you end up with thick elements being averaged with thin elements, and that's never a good thing. So again, by default, the property is turned on here, so only elements with the same property are averaged together. So that's a really nice thing. One other thing I wanted to show quickly, so I don't run out of time here, is that when I wanted to set up my parameters to choose the different output file types, it's under Output Control Directives. And if I just click on this, it pops up the NashTran Online Help. And this is the NashTran Help, and it tells me what all the options are. And something else that's always nice up here is I can go to any of my bulk data entries and look up what they actually mean within the online help system. And so it's easily accessible within the reference manual. The user's manual has a bunch of examples in it. So when you're wondering what you're doing, you can do all those things. So again, if I want to change my result file type to an OP2, I change it to NastRan binary, I run the job, and I'm going to get a OP2 file out of it. Similarly, it's under results processor parameters down here. There's param post, and I can set it to -1 for something like Patran, or -9 or 10 if I want everything out of there. So that's where you get that. the last thing I'm going to touch on right here is I can change my model tree up here to be the Autodesk NashTran file, and if I don't have it, I can run it, I can save it, I can insert new cards, or I can update it, which is what I'm going to do here. And so here's my NashTran file, and I could look through my NashTran file and see what is in this file that's important, that relates to my things. And I can see up here my output requests are for plot only. If I were to change that to print, I would now see it says print up here, and we'll get that. Similarly, if I wanted to do it, I could either use the parameter, or I can go up here and I can insert a new card, and I can tell it it's free format, and I can say NashTran RSLT file type equals, and say OK, and it'll throw that card into my file, and now it'll run and it'll do the same thing as toggling the parameter, only it's now part of your NAS file. So when you write out the NAS file, it's actually in it. So that's all I had to show for this. So let's go back to our little presentation here and open up the floor for any questions that people might have.
Thanks, Bart. We did have a question coming in here from James. So James is wondering, you had mentioned a little bit earlier about using the output files to diagnose convergence issues in a nonlinear analysis.
Oh, yes.
He's wondering if you could just go over that a little bit, maybe highlight that workflow.
Sure, and I think I have that right out here. Here's an out file from that. This is the tank. This is a linear static one. Let me open up the one from the other one that I had, which is going to be in a different place. This is going to be under here, under May. No, all files. No, this is, yeah. Where is it there? Maybe it is under here. Let's find my file. I wanted to look at the the file and see where it is up here. I've got one here somewhere. I thought it was right here. Maybe it's here. Oh, here it is. Let's pick one of these. Let's go to, I'm just going to look at one of these here. This is one that we ran. That's analysis 2. Let's pick the output file here. When I run, here's what I want to show you. Here's the weight generator for this particular model file. This is a nonlinear analysis. And so with each time step, hopefully people can see here, time step, time 0, time step 1, it gives me a little summary of stuff that's in the output file here. And there's 3 different convergence criteria. There's displacement, load, and work. And for each one, it tells me the absolute error and the convergence percentage. This one isn't very nonlinear because it's time step 0. But as I go down to time step 2, I can see time step 2, the first iteration, the displacement and the load converged, but the work did not, because I have 100%, 100%, then 21%. On the second iteration here, counting down here, all 3 of them converged, and it said great, and it went on to the next step. Usually on nonlinear analyses, let me see if I have one of these that goes on, that goes on longer here. It'll give you a summary of all these that go on for quite a while, and you'll be able to follow through and see what my, oh, sorry, wrong file. Let's see if this one gets more nonlinear. Because often there'll be a whole stack of these iterations. You'll have 15, 20 iterations on on one. And what you'll often see is you'll see the percent will be like, 0, 0, 0, 0, maybe 100, and then this one may be 0, 0, 100, 100, 100, and work may be 1, 1, 5, 5, 10, 10, 10. And you'll often be able to look at it and say what's converging and what's not converging. And there's certain types of analyses. By default, we look at load and work, but there's certain types of analyses that the load will never converge on. And if you look at your iteration summary for a crashed run, you'll see that the displacement converges, the work converges, and the load just never converges. And so that's a big flag for you to say, hey, I should not be using load convergence, let me change it. And so that's where you go back into Inventor here and back into my model tree and go into my nonlinear setup here and my advanced settings. Here are those 3 convergence criteria. By default, we do these 2. But if load is not convergent, I can uncheck it. I can change it to displacement. I don't have to put in values. It'll choose the defaults if I don't. It doesn't necessarily affect your analysis and the accuracy. A lot of it's just numerical techniques that let you do that. So that's what I got. What else we got?
It doesn't look like we have any more questions at the moment. So if anyone does have any questions, you can use the there's a bar on the right-hand side where you can enter any questions you may have, not necessarily related to the presentation today. Anything you want to ask about NashTran In-CAD, we'll be glad to answer those questions.
Yeah, it's a tech forum. Doesn't have to be this this topic.
So Bart, one new feature related to results in 2016 maybe you could highlight is the query. It's a little bit more accessible now, I think.
Yes, it is. And that's when I have a result on here and I'm plotting on here. Let me reload my results because I got out and got back in. When I have some kind of result plotted up here, let's go with my von Mises stresses. If I want to actually know what the values are that FMAP is plotting, I can go over here onto my nodes, for instance, and say query display. And as I hover over a node, it tells me what node it is, and it tells me the value that it has. Sometimes it's a little hard to see, but you can squint at it. If I go over here, it's much easier to see. And it'll tell me the total translation, the X, the Y, the Z, and because I'm plotting nodal stresses, it'll tell me the solid von Mises stress that was actually calculated at that point. So if I find my minimum right here, it should tell me that the minimum is 7146, which is exactly what it is. It's actually 7145 point blah, 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 blah. And that's what it's actually plotting there and tells me what the minimum is. The query display is pretty cool because it lets you do this kind of thing. You can also go to Elements and turn on the query display for the element, and it'll tell you the same thing. I can pick an element here, and it tells me the solid von Mises stress, which is the centroid value, and then it will tell me the solid von Mises stress at all 10 nodes of that particular element. So it's sort of a nice way. I often find when I'm using it that I have to zoom in quite a far in order to pick the element that I want in order to read it, but that's not so bad, not such a bad deal. But again, the query display works really nice, and it goes along, it highlights the element. You can use a screen capture, is it like Control-Shift-P or something, get a screen capture that I can then put into a report type thing. So there's a number of nice things that come about with the query display.
Yeah, and that's all now. You can pull that down with the probe option at the top too, I believe. So on the ribbon.
On the ribbon. There it is. There we are. Yep. Yeah.
And I'll give you the same functionality there.
Okay.
So we did have another question come in. And we're interested in extracting forces versus displacements as a graph from a nonlinear simulation.
Displacements are certainly what you will get if you do forces is, unfortunately, when you run forces, they're element forces, not nodal forces. And For bar elements and rod elements, and I'll call them one-dimensional elements, forces are nice and easy to extract. You can use the query display. You can use printed output. It's pretty good. For solid elements and shell elements, forces are a little harder. And the reason I say that is because forces are, in shell elements, for instance, are output as a force per unit length. So if I pick an element and ask for the force in it, it'll tell me it's 16. But that doesn't mean I've got 16 pounds in that element. It means the element in the direction that the force is calculated is 16 pounds per inch along the edge of it. So the forces for plate in solid elements are it's force per square or whatever. They're much harder to use element forces for three-dimensional elements. I'm not sure that answers the question, but if I want to do things like that, I can do that. Let's see, what do I have on this one? Do I have multiple increments? Ah, shoot, I only have one increment on this one, which is another thing. If you run a nonlinear analysis, I almost always turn my intermediate output to on or all. That way I get increment 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And so if my run doesn't make it to 10, at least I have a result. It also gives me the ability to watch the nonlinear deformations in a static analysis as I apply the load in increments. So, oops, let me get out of that. Okay. Anything else?
So we got another question here from Thomas. When you see the query display for nodes and the node numbers are shown, how do you count the nodes?
Oh, how do I tell which is which? With great difficulty. There isn't really a good way. The way I tend to do it is, and in fact I did it on that tank that I was going to show people, is I wanted to know what these two elements were. So I went into my element query display and I said, this is element number, what is it, 8249, 6249, 8249. A little hard to read there, 8249. And it tells me what all the nodes are. And there isn't a good way to do it other than going into my node query over here and then saying, okay, that node is that, and this node is that. That's probably the best way to do it. If I'm doing a limited number of elements, here's the mid-side node, 11041, here's one end node, here's the other end node. So you can use the query without a result to find out what the nodes are. And unfortunately, that's probably about the best way to do it for now.
So James has a question here. He's getting a specific error message about material specified and field 2 not compatible with failure theory, and he's looking for information about how to find out which material it's referring to. So if I had to guess, James, I'd imagine that the material setup you set up there, one of them is referring to the MCT failure criteria, which is not part of Nastran In-CAD. So if you have a material set up with that failure theory, that's what's going to be generating that error message. Let's see, it looks like we got a few more questions here. Okay, so it looks like regarding the graphing the force versus displacement, he's looking for to graph it at a specific node or point here, and I don't think that's something that we can do in In-CAD.
No, it's something I've done in FMAT before, but I don't believe it can be done in In-CAD, where I can choose a specific location and plot it as along a curve or along something. I don't believe that's. I think that's one of our. I think that's on our to-do list, but it's not on our done list.
Yep. So let's see. It looks like one of the other specialists here, David, had a comment about the failure theory. He said you could also possibly be using an isotropic material, and you may have an orthotropic failure theory defined there. So that could also be generating that error message.
Yeah, I have gotten that error when I've made composites laid up out of, I'll have a layer of like aluminum and then a bunch of layers of fiberglass, and I'll have a Psi-Wu theory chosen, and it gets to the aluminum and goes, Psi-Wu, aluminum? I don't know what to do with that. So yeah, I think that's where I've gotten that one too, when I tried to use just plain the wrong theory for the wrong material.
Let's see. So again, if you have any questions, you can use the sidebar there to enter them. Looks like we got another one here. Is there a way to activate the plotting of contact force for a linear static analysis?
Let's see, the contact force for a linear static. I don't know whether, I think it's in there, and this is a nonlinear static, so it's going to have it. But if I go into a linear static, let me look at my results here. Let me go in here, and I believe even in a linear static, it will list up here the shell contact pressure. I believe it will do even in a linear static analysis. I think I get the shell contact pressure, or either that or the contact force. It may just be the contact force that I get. Oh, no, yeah. And you should get it all. And there's the contact traction X and Y, which are in the X and Y directions, parallel to the surface. And then you get the force that's normal to it. And I think that's either this one or this one. One or the others you actually get in the linear static analysis. And I say that because I did that the other week, and I was trying to get this particular model overlapped too much for the linear static to work, so we had to go nonlinear.
So it looks like as a follow-up to that question, when the user plots it, it's not actually generating anything, and I was wondering is there any kind of key to activating that?
Now, as long as you're asking now, because it's requested, as soon as you put a contact in, it requests the forces automatically. I believe those forces get generated whether you ask for them or not. That was an Autodesk NashTran thing. I don't know that you've run across this, Andrew, but I don't believe you even have to ask for forces in order to get that.
No,
I think it generates it automatically.
Yeah, in my experience, it'll generate that information automatically. So, I mean, if it's not generating any information there may not be any contact occurring.
Yeah, it may be zero. Yes, because NashTran has a terrible habit of if you get zero results, it just doesn't create them. So you run a model without any loads on it, and it runs, but it doesn't generate any results. You're like, why don't I have any results? And, oh, there's no load. So I've had that happen too many times to count. And it may just be that there's no contact occurring, so it's all zero. So you're not getting that vector because there is no contact.
All right, well, it looks like we're at the top of the hour here. So I just want to thank everyone for attending our session today. Like I said at the beginning, we'll be having a session next Wednesday at 11 with the product manager, Mitch Muncy, going over what's new in Nastran In-CAD 2016 as well as Nastran 2016. The following week on Tuesday, we'll be continuing the Build Your Nastran IQ session with a discussion about contact analysis and some of the settings and parameters there that you can use to get your models running. If you have any follow-up questions, you can always post them on the Nastran In-CAD forums, or if you've got a more in-depth problem, if you're on subscription, certainly don't hesitate to open a support case through the Autodesk account portal. All right, thanks for attending, everyone, and hope you have a great week.